Hello and welcome back to Complex Differential Geometry. Today we're going to be doing Lecture 9, which is Connections, Curvature, and Churn classes. But before we get into it, as usual, let's do a little recap. I'll try to keep it brief this time. So last time we did Lecture 8, which was on Dolbeau cohomology. So let's review a little bit of what we did on Dolbeau cohomology. We looked at the idea of obstructions. Obstructions were failures. Well, they were the things that caused the failure for a locally solvable problem on the manifold to be a globally solvable problem. And then from there, we looked at what equations we were trying to solve. So they were like this. There exists alpha such that omega is equal to d alpha. With the other equation that d omega is equal to 0, we wanted to solve this for omega. This would give us the de Rham cohomology group. We were looking for closed forms that are not exact. De Rham cohomology group. That was given by HK dr. So that would be the kth de Rham cohomology group. Similarly, for the complex case, we had there exists alpha such that omega is equal to partial bar alpha. This was the adjoint Dolbeau operator. And we were also solving it in the context where partial bar of omega is equal to 0. So this gave us the Dolbeau cohomology group. So these are like the real and complex analogs of each other. And we denoted that as this. HPQ partial bar of M. So there's another version that's conjugate to this that it looks like H partial PQ of M. And together these, so okay, before I get to that, this gave us topological obstructions, which are basically holes. So this would give us K holes. And these would give us complex analytic obstructions. This one specifically would give us, so this one would give us holomorphic obstructions, and this one would give us anti-holomorphic obstructions. And you can think of that as, instead of there being a literal hole in the manifold, there's a patch of the manifold that causes the holomorphic coordinatization to fail, and therefore we cannot define a global PQ form on that manifold of that type, of that PQ type or PQ degree. So we looked at that. We looked at Dolbeau's theorem, and de Rham's theorem. And these are the complex and real analogs of, so this is isomorphic. So these groups, right, the de Rham groups are isomorphic to singular cohomology. And these groups are isomorphic to the Čech cohomology. Which was also called sheaf cohomology. And this was kind of just like a formalization of the fact that these groups do indeed capture the local to global patching idea, and that the non-triviality of the group is what indicates the existence of an obstruction to solving these equations globally when they can be solved locally. And the local solutions are guaranteed by these two lemmas, Poincaré's lemma and Dolbeau's lemma, in the real and complex case respectively. And so once we established Dolbeau's theorem, we looked at some examples of Dolbeau cohomology group. Specifically, we looked at CP1 and complex T2, which I wrote like this, or complex T1 actually. So we saw that their Dolbeau cohomologies were different, especially H10 and H01 were different for these two. For CP1, they were 0, and for the complex torus, they were 1, the Hodge numbers. Oh, I forgot to talk about the Hodge numbers. So the dimensions of these groups are called the Hodge numbers. So that's HPQ. It's called the Hodge number. And the dimension of this group is called BK, and it's called a Betti number. And BK is actually the number of K-holes in the manifold. Right, and then lastly, we looked at these things called Hodge diamonds, which is a nice way of arranging these Hodge numbers like this. You start with H00, and then you increase the P grade, the holomorphic grade, in the when you go to the left, and you increase the anti-holomorphic grade when you go to the right. So it kind of looks like this, and then if you have one more over here, then you get 0, 2, and then here you get 2, 0, and then here you would get 2, 1, and here you would get 1, 2, and here you would get 0, 3, etc., etc., and it would keep going. And it's a diamond because it goes, it gets as big as it as the dimension. So like here it's 3. Here the dimension, the complex dimension would be 3, and then it would start narrowing and go back to a point. So that's what we did last time. Now let's move on to talking about connections. So before we get into the formal definition of a connection, let's kind of try to get an intuitive idea of what are the topics we're going to try to cover today. So our main reason for defining connections is going to be that we want to be able to define the derivative, right? We're doing differential geometry, so we want to define the derivative of an entire vector field. And this vector field doesn't necessarily have to be a tangent vector field. We're going to depend on a generic vector bundle. So this could be a vector field over E. E is going to be the name of our vector bundle. This is an abuse of notation that we're using. E is actually the bundle space, right? Not the vector bundle is the triple, and we're basically just calling E the vector bundle itself because that's like the space that we're talking about. The other two are the manifold and the projection map. So we're going to call E the bundle from here on out. So what does that mean? Well, let's draw. I'm going to draw a bean-shaped manifold today because it catches my fancy. So let's say that we have two we have 2 points on this manifold M. That's the base space. So obviously we have these 2 fibers jutting out from these 2 manifolds, and let's say that we have a vector field X, which is an element of the smooth sections of E. Right? It has to be smooth because we have to be able to differentiate it. So we make a choice on each of these fibers of XP and XQ, right? These are the vectors that are being assigned to by X for these 2 points, right? And whenever we want to define something like a derivative, what we want to do is to take 2 close by objects, in this case of vectors, and then we want to subtract them, and we want to take the limit of that difference, right, in order to define something like a derivative. Now the problem is that P and Q, these points have fibers or vector spaces that are completely separate, right? They're different universes. They don't interact with each other. So in order to actually define what XP looks like in XQ's point of view, we need some sort of definition for that, right? We need to define it as something. Right now, we don't have anything. And so that definition comes down to the definition of a new object called a connection. Literally, because we're connecting the two fibers. The connection is a kind of derivative because it tells us how XP changes as we take it to XQ, as we take it to that other fiber. And as we take these fibers closer and closer together, we can form this limit that is going to give us what the connection is. We don't, in practice, define the connection that way, but this is the intuitive picture of what the connection is trying to tell you, is that it's connecting these separate fibers together, right? And that it's a derivative. So before we move on, one thing I would like to emphasize is that in the live recording, I said that I talked about E as though it was the tangent bundle. This doesn't have to be the tangent bundle. It could be any vector field over any vector space, right? And secondly, that this definition is over a vector bundle, right? This is the main object. So the central actor in this lecture will be the vector bundle. So whenever we're talking about connections, you have to think of them as being defined over a vector bundle. So once we have a connection, we can think of this idea of curvature on a manifold. So we think of manifolds as curved spaces. It's the connection between the fibers that allows us to talk about their curvature. So to get an idea of where curvature comes from, let's draw a sphere and a flat plane. Now I can draw a triangle on both a sphere and a flat plane. I'm going to draw a big triangle to make this more obvious. And we're going to use the connection to connect all of these vector spaces that are along this triangle. At each point on the triangle has its own vector space attached to it, right? Its own fiber. And let's see what we can do with the connection. So one thing we're going to do is we're going to try to keep the vector as straight as possible on our curved surface. And we're going to see what happens when it goes over a complete closed loop. So let's say that we have this tangent vector to start over here. And then as I'm a little ant on this manifold, and I'm moving this tangent vector along my curved surface. So what happens? The tangent vector is going to curve down, right? And we're going to try to keep it as straight as possible. We're going to try to make sure that we minimize the change in direction. So that's what it's going to curve down along the manifold. And then now it's pointing straight down, right? Now it's going to be pointing straight downwards by the end of it. Along this curve that's curving around the equator, it's not really going to change because it's perpendicular to the curve, right? But then once we go backwards along this other curved side of the triangle, we're going to see that, okay, I'm going to now draw it in a different color so that I can highlight the fact that it's now a different vector, right? So see that these two vectors are not pointing in the same direction, right? And that's what is a clue for telling us that this is a curved surface. But which, for example, if I were to draw a vector on this surface, if I were to try to keep it as straight as possible, I would do this. It would be very easy to keep it straight because I'm on a flat surface. And once I finish that closed loop, what I would find is that my vector hasn't changed. So it's this change in the vector that's telling us about the curvature of the manifold, right? And this is before we have a metric or anything. All we need is there to be a connection. The connection is on the vector bundle. And then the connection then gives us this idea of what we were doing right now, which is called parallel transport. we're trying to keep the vector as straight as possible. Parallel transport. And then we were thinking about parallel transport across a closed loop, which would give us this idea of curvature. And the important thing about this idea of curvature is that it's intrinsic, which means, right, so we have this external space. I'm going to draw it like this. Let's say that there's this cube that is enclosing our sphere. It's also enclosing this flat plane as well. But this is called the ambient space. Ambient space. And the ambient space is higher dimensional, right? So our manifold is 2-dimensional. It's a sphere. The ambient space is 3D. What we want to do is to come up with a definition of curvature that doesn't depend on the ambient space. Why? Because we don't always have access to the ambient space. For example, in physics, we think of space-time as a 4D manifold, and how are you going to get outside of space-time? You really can't. You can't go outside to look at the curvature from above. So you need this like worm's eye view of the manifold, like you're a little ant or a worm on the manifold, and you need to be able to tell that it's curved from the manifold. And the fact that if you move a vector in a closed loop and it will change direction, you can tell from an extrinsic point of view that is telling you the curvature. So then, without even looking at the ambient space, if you can define a connection, then you can figure out whether a manifold is curved without actually going to that bird's eye view in order to be able to look at it, which is extremely important for certain use cases, and makes it so that we don't have to exit the manifold in order to define its curvature, right? Sometimes an ambient space is not going to exist, and so therefore it's important to be able to come up with an intrinsic definition of curvature. Once we have curvature, we get this interesting class of topological invariants called Chern classes. Chern classes are going to be important for us because they're important to Kähler and Calabi-Yau manifolds. And they basically capture this idea of twisting of the vector bundle. And we also compute them using the curvature, and therefore they depend on the connection. Ostensibly they depend on the connection, but as we'll see, C1 of E, the first Chern class, is actually its dependence on the connection drops out, and so it becomes a really powerful topological invariant of the manifold that can be calculated with any connection, and then it'll give the same result. And this is very directly has the interpretation of giving us the twisting of the vector bundle. So now that we've given a high-level overview of what we're going to cover, now let's get into the formal definition of something called the Cauchy-Zuul connection. So what is the Cauchy-Zuul connection? Cauchy-Zuul connection, which from now on we're just going to call it the connection. It's not a special type of connection. It is just a way of defining connections. So this is a map. We call it nabla. It goes from smooth sections on E. That's what we're trying to differentiate. That's our input. And it takes us to smooth sections on E that is tensored with omega 1m. So differential one forms. So the way you can interpret this is that you have a one form that takes a direction and will give you a derivative in that direction. In this case, because it's a one form and not an exterior form on a single point, it gives you a derivative over the entire manifold given a vector field, but then it's multiplied by a coefficient, quote unquote, that is a vector field on E, gamma of E, which gives you something of the essence of the weight of that vector field in that direction, or of the derivative vector field in that direction. So what we want at the end of the day is for the derivative of a vector field to be another vector field. That makes sense because the rate of change of vectors at every point on the manifold for a specific vector field should be a vector at each point on the manifold. And we're going to impose on the definition that that rate of change has to be smooth, so that the derivative of a vector field is again a vector field, which would be nice for geometric reasons, so that they're both geometric objects. So this thing is, we might call this a vector field valued one form. So this makes the connection a kind of universal directional derivative. What do I mean by that? I mean that the connection can take one, a point on the manifold, and two, a direction associated with that point, and then it will give you a derivative, an actual scalar number associated with the rate of change, right? At that point, at that direction. So it stores the derivative in every direction of every point on the manifold for that vector field that was the input. That's what the connection actually tells you, and that's why it acts like a derivative, or like that's the intuitive idea behind why it's acting like a derivative. Now, before we formalize why it's a derivative, let's look at some of the properties. Number one, it's R linear, which means that nabla of A S1 plus B S2 is equal to A nabla of S1 plus B nabla of S2. And this is required by definition. And number two, we require it to be a derivation, which means it needs to satisfy a form of Leibniz rule. So its Leibniz rule looks like this. Oh, obviously here I forgot to mention A and B are elements of R. That's the whole point of being R linear. So here, if we have nabla of F times S, where F is an element of C infinity of M, obviously the real form of it, and S is gamma of E. So the way we decompose this is we say that we first differentiate the first one, leaving the second one, plus we leave the first one and then differentiate the second one. You could think of that as saying that nabla of F is equal to D of F, right? So that is the Leibniz rule. So then one thing we could do is we could think of nabla as something that takes two inputs, right? It takes X and it takes S, right? And let's say that, so X is a section of the tangent bundle, this time for real the tangent bundle. So we define something called nabla X of S as being equal to nabla of S. This is a vector field being applied to a form, right? So the way we can think about this is that nabla of S is an element of gamma E times omega 1 M, right? Which is really just a way of saying that it's a smooth section on the cotangent bundle, right? So if we took this right? The elements of the cotangent bundle, the forms, they are functions that map vector fields, right? So then if X is a vector field, then these will annihilate. This gamma of T star M will annihilate with this gamma of Tm. And from there, we will get a value, right? The value will be, so it will annihilate this part. So that value, the vector value, will result in another vector field. So this is, in the end, how we get a vector field from the connection, right? We said that we wanted a derivative that would take a vector field and give us a vector field that represented its derivative. So this derivative is called the covariant derivative. Because it takes vector fields on the manifold, on the vector bundle of the manifold, and returns vector fields, geometric objects, you could say that this is the natural derivative on the manifold. And so this idea of covariant derivative is really trying to come up with a derivative that respects the manifold's vector bundle structure, right? So that's what we're getting at here. And so at the end, what I would like to say is that nabla x, the covariant derivative, is a map that takes us from smooth sections on E to smooth sections on E. In other words, vector fields on E to vector fields on E. And particularly, if nabla x of S is equal to 0, that means that S as a vector field does not change along X. If you think of X as a flow field over the manifold, right? X applies or assigns a vector to each point on the manifold. If you take all those vectors, you can define a flow on the manifold. Because X has to be a smooth vector field, this assignment is smooth, so there's a smooth flow. We're saying that along that smooth flow, S does not change. So that's what we're saying. S does not change along X. If you think of X as a flow field, or let's say a flow vector field. So that is the definition of the Cauchy-Zuul connection and the covariant derivative that you can define off of that. So now what we're going to do is we're going to look at some of the properties of the Cauchy-Zuul connection that enables us to think of it as a valid directional derivative. We called it a universal directional derivative. What is the justification for that? Well, we really need three properties in order to call something a derivative. Firstly, we think of derivative operators as, if we take the derivative of 0, that we get 0, right? Okay, so what does this mean in terms of the connection? So let's say that we took the linearity property of the connection. We said that nabla of minus s, right? We know that this is equal to, so this minus 1 in front of the s is equal to a. So a is equal to minus 1. So then we get, and b is equal to 0 in this case, right? So in that case, we get minus nabla of s, right? But if we say that S is the 0 section, what is the 0 section? The 0 section is the section where we've assigned the 0 vector at every fiber over the manifold, right? If S is the 0 section, then we find, we're going to call the 0 section this fancy 0. So then nabla of fancy 0 is equal to minus nabla of fancy 0. Because for the 0 section is the only section for which S is equal to minus S, right? So then we get this relation, which we wouldn't have gotten for any other section. For any other section, these are not trivially related. This has the very famous format of A is equal to minus A, whose only solution is that A is equal to 0, right? Which means that nabla of 0 is equal to 0. And that's why I wrote the fancy 0 here, because I didn't want you to get confused between the 0 section and the number 0, right? The real number 0. So that's something that we get. And this is property number 1 that makes it behave like a derivative operator. And then number 2 is that it is local. We can show, I'm not going to prove it here, but if S1 restricted to some local patch of the manifold is equal to S2 restricted to that same local patch, that implies that the nabla of S1 restricted to U is equal to nabla of S2 restricted to U. What this means is that we can define the connection on a local section as opposed to a global section, and that this definition, so this definition is independent of the choice of extension. So the way we're defining it is that we're going to say that nabla of S of P is equal to nabla of S tilde of P, where S tilde is is an extension of the local section to a global section. And what I was saying here before I cut myself off is that this definition is independent of the choice of extension. So this is well defined. So that means that this operator is local. It only uses local information. It doesn't use information from the totality of the manifold. It only uses information from a arbitrarily small neighborhood around the point that we're interested in. Number 3, if you think of nabla as a function of 2 variables, then it is C infinity linear in its x input. Which means really that if we think of it from the point of view of the covariant derivative, we don't have to actually. Let's just say it like this: fx plus gy, where these are both C infinity mr. Then we can say that f nabla of xs plus that this is equal to f nabla of xs plus g nabla of ys. So this means that it is defined pointwise on each P and M, which is also what we expect from a derivative operator or a directional derivative operator, that it only depends on x at or on the flow vector field at the point P. So these 3 are in fact enough to tell us that this connection acts like a derivative operator. So now that we've defined the why, or we've looked at why the properties of the connection tell us that it's a derivative operator, let's look at a specific kind of connection that's going to be important, called the affine connection. The affine connection is basically just this idea that what happens if we, instead of taking E, we actually take the tangent bundle. So here we're actually using the tangent bundle. And if we take the tangent bundle, then this connection becomes the affine connection. And a manifold with a vector bundle that has an affine connection on it is called an affinely connected manifold. And the affine connection is special because all that stuff that we were doing at the beginning with the parallel transport and all that stuff is that we needed to connect the tangent spaces in order to do that, right? We were using tangent vectors. So without the affine connection, parallel transport, geodesics, these are not well defined. We don't have time to get into all of that stuff, but if you want to read more, there are a bunch of physics textbooks that go into this, like Misner, Wheeler, and Thorne's book Gravitation. That goes into parallel transport. I think it's in chapter 10, and Ryder goes into parallel transport in chapter 6. Unfortunately, I haven't gotten a lot of resources, or haven't found any resources where they're talked about from a purely mathematical point of view. If you know any resources like that, please do leave it in the Discord server. But the important thing about affine connections that we need to define is something called torsion. So torsion is a tensor T. It takes two vector fields, and it takes you first you take the covariant derivative with respect to x of y minus the covariant derivative with respect to y of x, and then you subtract off the Lie bracket of x and y. So this is called the torsion on the manifold. If this is non-zero, then it represents the failure of the covariant derivative, and by extension the connection to be symmetric in its two vector field inputs. And so that kind of induces some kind of tension in the manifold that is called torsion. And if you remember in lecture 5, we were saying that the Nienhaus tensor represents a kind of torsion, and it's actually linked to this torsion on the affinely connected manifold. In the presence of a metric, I'm pretty sure the first term of this torsion tensor actually turns out to be the Nienhaus tensor. So when we take the connection to be a specific kind of connection that we're going to look at next time, called the Chern connection, that's going to be the case. And so this the Nienhaus tensor and the torsion tensor here on the affinely connected manifold is actually very closely related to each other. So that's why I was saying that the Nienhaus tensor represents a kind of torsion. So there's a special case here where Txy is equal to 0. This makes a manifold with a vector bundle where the connection's torsion is 0 is called a torsionless connection. Torsionless connection. And this is a special class of connections that is going to become relevant to us in the future, in the next few lectures. So I wanted to define this, and remember, why did we need an affinely connected manifold to do this? Well, look here, we have the Lie bracket. The Lie bracket is only defined using tangent vector fields, right? And because we have a tensor T, it can only have two, its inputs can only be either tangent vector fields or not tangent vector fields. So if this has to be from TP, or if this has to be gamma of Tm, then you can bet that these also have to be the same thing, right? So, but that means that this nabla has to be defined over tangent spaces, and therefore E has to equal Tm, right? So torsion is only definable on affine connections and affinely connected manifolds. Now that we have that out of the way, we would like to define local frame fields. But wait, we already defined local frame fields in lecture 4, right? Well, the thing is that I moved local frame fields from lecture 4 to lecture 9, where the reasoning for that was that local frame fields never became relevant until lecture 9. And I felt like even though local frame fields are fundamentally a vector bundle concept, and that's what lecture 4 was about, they actually only get used in lecture 9 once we start trying to decompose some of our vector fields in terms of a basis, right? So we're just going to do a short review of local frame fields here. So we know that local frame fields are bases for vector fields. So they're made up of local sections. So what is a local section? A local section is a map S that takes you from U, which is a subset of the manifold, to the vector bundle. But this definition is a little bit too loose, right? Because what we really want is to be able to assign a point on U to its own fiber, right? So really we want to do something like this. The way we enforce that is, well, what we want to do is, like, if this is in P, then this is from EP, right? So in order to enforce that condition, what we say is that pi after S is equal to the identity. What this enforces is that if I have this set U, a subset of the manifold, and I have a point P from which I have a fiber, then pi is a map that takes us from the entire fiber back down to P, right? So that forces us that if the result has to be the identity, then our map has to map from P, our map S has to map the point P to somewhere on the fiber. So this is, we'll call it SP, our choice of vector for P. So since our local section is supposed to represent a choice of vector for each point, we use this condition to make sure that each point has a vector from its own fiber. So then an LFF is just a collection of these S alpha, where S alpha is a map from U to E, right? So it runs over all the dimensions of the vector bundle. So if the vector bundle is a q-dimensional vector bundle, then alpha goes up to q, right? And the only thing that restricts the choice of these local sections is that they have to be pointwise independent. Meaning their restrictions have to be independent. S alpha restricted to P. This is a vector, right? If S alpha is a local section, then S alpha restricted to P is a single vector. And those vectors have to be independent, which makes sense if they have to be bases, right? Because bases have to be made up of independent vectors at each point. So that's what a local frame field is. So now that we have a local frame field, we can use that in order to decompose our connection into a bunch of coefficients. That's called connection coefficients. So we're going to say now that, let's say that we have a local frame field. We're going to call it E alpha, where alpha goes from, we could write it like this: alpha goes from 1 to q. This is our local frame field. Each of the E alphas is a vector field. They're all pointwise independent from each other. So in that case, we can say that nabla of E alpha is defined to be omega of alpha beta tensor E beta. Where a more common way of writing that is just writing them juxtaposed next to each other. So this is what we're going to say, and these are called the connection coefficients. Connection coefficients. And so remember that this object had to be gamma of E tensored with omega 1 of m, right? So this is our omega 1 m part, and this is the part that comes from gamma E. Now I know what you might be thinking. Well, this is just the basis for gamma E. Well, where's the rest of it? Where is the component that is going to be multiplied, right? Because a vector is equal to SI EI, right? So where's this component part? Well, we can think of that as being absorbed into the coefficient of omega alpha beta. So that's kind of how we're defining these. And one important thing to realize here is that alpha and beta are not tensor indices. They are not, this is not telling you that it's a 2 form, because obviously it's a 1 form, right? These are matrix indices. And the reason that I made them downstairs and upstairs is just because it's easier to keep track of which index is multiplying which index if one of them is upstairs and one of them is downstairs. So omega is not a tensor. Omega alpha beta is not a tensor. It's not a 1-1 tensor anyway. So, or it's not a tensor at all, and it's definitely not a 1-1 tensor. So these are matrix indices, not tensor indices. We can write so this is the notation that Chern, Chen, and Lamb uses. In modern parlance, this would instead be written something like nabla of E, where you can think of, instead of calling this LFF, let's call this E. Nabla of E would be equal to omega dot E. That's how we would write it in the common day. And since these are both matrices, right, this is a matrix, and this is a vector. So therefore, this multiplication is sort of like a matrix multiplication. Okay. Each of the components of omega is a 1 form, but it is a matrix of those 1 forms. That's why alpha and beta are not tensor indices. So now that we have this thing, so what is omega, right? Omega is called the connection matrix, or some people just call it the connection form. The reason for calling it the connection form, and that's what we're going to be calling it too, is that you can think of it as a form whose component or whose coefficient that's multiplying it out front is a matrix. It's a matrix multiplied by a 1 form. That's how you can think of it. So that's why we might call it the connection form. So now that we have the connection form, we can use this to define curvature. So let's talk about curvature. Curvature is in a coordinate independent way defined by something called the curvature tensor. This is not the Riemann curvature tensor. This is pre-metric, so we don't have a Riemannian manifold. This is a different curvature tensor, and this curvature tensor is more intrinsic in the sense that you don't need a metric in order to define this form of curvature. And remember, at the beginning of this lecture, we were saying that you don't need a metric to define curvature. You just need parallel transport. And parallel transport only needs a connection. And so if you can define a connection, which you don't need a metric to define a connection, you can define curvature. So don't make the mistake that, because I have curvature, that means that I'm in a metric space. So this is defined as nabla x, nabla y, minus nabla y, nabla x, minus nabla of the Lie bracket of x and y. This might remind you of the torsion definition, but it's slightly different. This expression is telling us that we are trying to evaluate the commutator for the covariant derivative itself when evaluated on 2 different inputs. And then this term exists to account for the fact that x and y themselves might not commute. So to subtract off that part of the contribution, so that we can just tell whether or not covariant derivative itself commutes for its first input. So this is equivalent to that kind of parallelogram that we talked about in lecture 5. So it's something like this. So you have nabla y, nabla x, nabla y, nabla x. There are these 2 different vector fields, and then we have to see if the parallelogram closes, right? But as we said that time, the parallelogram might not close because of the Lie bracket. So that's why we need, so it might not close because of this, but it also might not close because there is curvature. So we need to subtract off this part in order to find out whether or not there is curvature on the manifold. So one can show, and there are some calculations in the lecture notes for this, that f nabla of xy can be decomposed into omega of x and y, where omega is a matrix, matrix omega alpha beta of xy, where this is equal to d omega minus omega wedge omega alpha beta of xy. So for the full calculation, you can refer to the lecture notes. They should be available either on the Discord or on the or in the description. And the upshot of this calculation that I want to point out is that this is called the curvature form. It's a matrix valued, just like omega, small omega was a matrix valued 1 form, it's a matrix valued 2 form. How do we know it's a 2 form? Well, it has the exterior derivative of omega, and we know that the exterior derivative increases the degree of the form by 1. So here we get a +1. And also here we have two 1 forms, and two 1 forms wedged together. When you wedge two forms together, their degrees get added. So this is also a 2 form. So this is a homogeneous 2 form. So this is a matrix valued 2 form. That's what we get from here, right? In fact, omega, as opposed to, okay, they're both called omega, so I need to say the curvature form as opposed to the connection form is actually something called an endomorphism valued form. So what does this mean? An endomorphism is just a fancy way of saying a linear map that takes vectors in E, takes vectors in E to vectors in E. So it's this closedness that makes endomorphism valued forms special, right? And they're not tensors, but, well, why am I saying they're not tensors? Well, in fact, the way that capital omega, the curvature form, transforms is that omega prime, or omega, let's say omega in S prime, let's say that that's the local frame. And so omega in S prime is equal to A times omega in S times A inverse. What's A? A is the matrix that takes you from S to S prime, where these are two different local frame fields. So this is literally the basis change, the coordinate transformation matrix. The fact that the transformation looks like this means that it is an endomorphism valued form, as opposed to the connection form, whose transformation law looks a little bit more like this. Let me move this around so that I have a little bit more space. We'll write it here for comparison. This actually turns out to be dA dot A inverse plus A into omega S into A inverse. So it would be endomorphism valued if it just had this part, but it has this extra part in terms of the exterior derivative of A, and we know that if something has the derivative of the transformation matrix, then it cannot be a linear map, right? So linear maps never include the derivative of the map in them. And so one thing I would like to point out is that why are we calling this an endomorphism valued form and not just calling it a tensor valued form? The reason is that for it to be a tensor valued form, E would have to specifically be a the tangent bundle, and we're working in a space that's more generalized than that. We're working in a general vector bundle. If we were working on the tangent bundle according to our definition of a tensor, which was copies of the tangent space and copies of the cotangent space, then it would be a tensor valued form, which is a specific kind of endomorphism valued form. But because we are including other kinds of vector spaces other than just TM, therefore we need to call it something a little bit more generalized and accurate, which is why we call it this thing, an endomorphism valued form. So that's the idea here. And so now we're going to look at how to define the covariant derivative on these endomorphism valued forms, so that just like with the covariant derivative of vector fields, where we don't exit the space of endomorphism valued forms in order to define that in a way, like we can define the covariant derivative in such a way that it results in a derivative which is also an endomorphism valued form, so that like there's this closedness to the operator, right? So let's see how we can do that. Well, let's start with let's say that phi, capital Phi, is an endomorphism valued form. So then if we use the transformation rule to set the stage first in two different bases, what we have is that what we want, or what we would want to do, is we want to define something that looks like this. We want to define the covariant derivative of the endomorphism valued form in such a way that it also respected the same transformation property, right? So that's what we're going to look at. So if we start from here, this is going to be a bit of an ansatz solution, but if you bear with me, then we will be able to prove this. The trick is first to take the exterior derivative. So if we take the exterior derivative on this side, we get this, just one form on this side. Here, though, we have three things being multiplied, so we need to use the Leibniz rule. So first we get dA wedge phi on S dot A inverse. Then we differentiate the middle guy, so we get A dot D phi S dot A inverse. And then we get the third term, which is -1 to the k A dot phi S wedge dA inverse, right? And this came from the way that the Leibniz rule worked, that respected the k grading of the forms, right? So at this point, what we need to do is we need to add something to both sides so that we get a format that looks like this. In order to do that, well, I know the answer. That's why we're doing an ansatz, a guess and check. The answer is to add this thing to both sides. We want to add minus omega wedge phi S, phi of S prime, plus -1 to the k phi of S prime omega prime, phi of S prime wedge omega prime to both sides. So what this will do is on this side we will get d phi S prime plus all of this, and we're going to say that that is equal to the covariant derivative of phi of S prime. And we're going to find that if once the dust settles, I'm not going to do the algebra here, because it's very involved and I might make a mistake. It's in the appendix of the lecture notes. I added it newly between this live between the time of the live recording and now. But suffice it to say that if we do the algebra, if we add these two terms to the other side and then we expand them in terms of omega and phi of s, then what we get eventually is a dot d of phi s. This is a good exercise. Maybe you can try doing this calculation yourself. And then if you get stuck, you can look at the calculation that I did. So yeah, we get exactly what we want, which is omega times phi s plus minus 1 to the k phi s wedge omega. Let me give myself a little bit more room there. I tend to write everything a little bit too far to the right into A inverse. So then we know that this again would be the covariant derivative of phi s, right? This is a little bit, I would say this is a little bit unsatisfactory for me to just tell you what the answer is, that we need to add this to both sides. I wish that there was a more convenient explanation for how we could have discovered that this was exactly what we had to add. And I'm pretty sure you can do that. I just didn't have the time to look into it, to look into a method for deducing that this was exactly the term we had to add to both sides to make it balance out and to get this form for us. But maybe I will add it to the lecture notes in the future. And when I do, you can have a look at how we might discover something like this instead of having to just know it in advance, know that it will work, and then substitute it in. So at the end of the day, what we got is that nabla of phi of s is equal to d phi s minus omega wedge phi s. I'm sorry, I keep putting the s inside. That's not supposed to be there. So plus minus 1 to the k phi s wedge omega. That is the covariant derivative of an endomorphism valued form. So if we apply this to omega, what happens? Well, firstly, we need to figure out what d omega is, right, in order to be able to calculate this. So let's calculate that. D omega is equal to d of d small omega minus omega wedge omega. That was the definition of capital omega, right, the curvature form. So if we distribute this, then we get d square of omega. Remember, d square is equal to 0, so this is 0, minus d of omega wedge omega. But d of omega wedge omega is equal to, well, we need to use the Leibniz rule, so we get minus d omega wedge omega minus omega wedge d omega, which means that this is equal to d omega wedge omega minus d omega, sorry, I wrote that in the opposite way. So that's omega wedge d omega minus d omega wedge omega, right? So let's go to the next page. So this essentially amounts to we can add and subtract omega triple product it with itself. So what does that mean? We can do this. We can do that, and then we can do this. Okay, let's write it like this: d omega. Just trying to write it in a suggestive form. That will make it easy to see the pattern. So then we have minus d omega wedge omega minus omega wedge omega wedge omega. So then these two will cancel each other out. So then we can extract out this distribution. So then omega wedge, I'm going for a specific definition here, right? So that obviously sorry, this should be the other way around. So this gives us this minus d omega minus omega wedge omega right? And this is again the curvature form. So d in all, d of the curvature form is equal to omega wedge the curvature form minus the curvature form wedge the connection form. So this is called the Bianchi identity. This is the Bianchi identity for the curvature form. And this is going to help us define, or it's going to help us calculate the covariant derivative of omega. So covariant derivative of omega is equal to d omega. It's minus omega wedge. It was phi of s, but in this case, phi of s is the curvature form plus minus 1 to the power k omega wedge. I have to stop saying omega. The curvature form wedge the connection form, right? So this is what we got so far. So what is that? So we can substitute what we have over here into there. So then what do we get? We get omega wedge. We get connection form wedge curvature form minus curvature form wedge connection form minus connection form wedge curvature form plus, well, in this case, k is equal to 1, right? Or k is equal to 2. So minus 1 squared is plus 1. So we get plus omega wedge or plus curvature form wedge connection form. And you can see that these actually cancel out with each other and these cancel out with each other. So we end up getting 0. So the covariant derivative, or sorry, I called it the covariant derivative. The connection of omega is equal to 0. This is a big result. And if we were to differentiate again, we would get that the second derivative of an endomorphism valued form, I'm not going to do the calculation here for the sake of time and because I don't have it. We're going to say this turns out to be this. You can also try doing the calculation for this. And we say that this is, we can think of the wedge product as a sort of multiplication, right? So then this kind of has the connotation of being AB minus BA. So this is actually a kind of commutation. So this is the commutator between phi s and omega. You'd probably want to call this omega s, but yeah, that's just reminding us which basis we are expanding this in. So that is it. That is the last property. So that's it for today. We've talked about a bunch of things. So let's recap before we move on to next time, where we're going to finish lecture 9. We're going to talk about connections and complex structure compatibility and holomorphic compatibility. So what did we do today? We defined connections, specifically the Koszul connection. It was a map nabla that took us from gamma of E to gamma of E tensored with omega 1m. And then once we restricted it, we got the covariant derivative, which was nabla of x, which took gamma of E to E, and to gamma of E. And this was essentially this idea that, okay, we have a vector field, we want to differentiate it. The connection tells us how to connect different fibers so that we can actually compare two vectors to each other. And then the connection, the map actually stores all the derivative information at every point in every direction. And then once we apply a flow vector field to it, which is x, it will actually turn into a derivative that when given a vector field will give us a vector field, which represents its derivative. And then we looked at the properties of these properties. We then looked at the affine connection. And in doing so, we looked at, most importantly, torsion, Txy. Specifically, when Txy is equal to 0, we get a torsion-free connection. Right? And then we looked at local frame fields. That was just a little bit of revision. Local frame fields. And we use them to compute connection coefficients, which when we put them in a matrix, we got a matrix valued form. Matrix valued form called the connection form, omega. And we used the connection form omega to define, well, we started off with f nabla of xy, which was the curvature tensor. And then we turned that into using, there was some algebra that I didn't do that would turn this into omega of xy, which was that was a matrix value 2 form, which looked like d omega minus omega wedge omega. And so this was not just a matrix valued 2 form, but an endomorphism value 2 form, because it had some additional transformation properties that was basically like omega in the S prime frame is equal to A into omega in the S frame multiplied by A inverse, which was different from omega, or sorry, I'm doing this again, which is different from small omega by the fact that it had this different transformation property. And then we looked at the connection applied to the curvature tensor itself, and we found that this is equal to 0. We also found the Bianchi identity, which said that the exterior derivative of this 2 form is equal to the connection form wedge the curvature form minus the curvature form wedge the connection form. And in the process, we also defined the connection as applied to any endomorphism valued form. That was d phi. I'm not going to write everything, or connection of phi is equal to d phi minus omega wedge phi plus minus 1 to the power k phi wedge omega. So that's all of the stuff that we covered today. Next time, we're going to look at complex connections. So far, there was no complex business going on. We were just looking at the real part. So complex connections. Specifically, we're going to look at J compatibility. And we're going to look at holomorphic structure compatibility. So J is on M, and holomorphic structure is on the vector bundle E. And then we're going to look at, lastly, Chern classes. So that's it for today. Next time we're going to do lecture 9 part 2. So goodbye and see you then.